Welcome to part B of Foley Lab Tutorial 7. So this is demonstrating a couple of features of Python, and in particular what we're going to do is look at Gaussian wave packets and their dynamics. So there was a part A that kind of gave a little introduction to the physical features of this problem, and what I'm going to do here is go through the first part of building this code where we're going to take a Gaussian wave packet given by this function here, and what we're going to do is we're going to expand that Gaussian wave packet and the basis of particle-in-a-box energy eigenfunctions. And then we're going to use the module matplotlib to plot both the initial Gaussian wave function and our fit in terms of the energy eigenfunctions to see how good of a job we did. So anyway, what I've got over here is I've got sort of my skeleton code in one terminal, and then I'm going to run Python in another terminal. And so there's a lot of different ways that you can execute Python and edit Python. I really like, sort of the standard Unix / Linux environment, so I'm doing everything from the terminal. So whenever I want to actually execute my Python code, basically all I'm going to do, my Python code is in this file pib_static.py, and I'm just going to call Python and then the name of the file to run it. And of course, right now, there's really no code to do anything, so of course nothing happens. And I say no code, I don't really truly mean no code. I sort of mean like no main code. I have a bunch of functions that I've pre-built that are going to come in handy, and let me just take you through them as I go through this outline. So what are we going to do in this step where we're going to build our initial Gaussian wave packet and then fit an expansion of energy eigenfunctions to it? Well, the first thing that we need to do is we need to create a grid of x values along which we're going to evaluate our various functions, our Gaussian functions and our energy eigenfunctions. So the very first thing that I'm going to do is I'm just going to create a grid of x values. I'm going to do 2,000 x values, and I'm going to create them between values of 0 and 500. And what that means is that basically my particle in a box lives between x equals 0 and x equals 500. I'm going to use atomic units in this whole tutorial. So what are the units of length here? Well, there are the atomic units of length. So 1 unit of length is 1 Bohr radius. Okay, next thing I'm going to do is I'm going to create an array which I'm going to call psi, and that's going to be defined as the Gaussian wave packet values. And so I've already built a function where I can give it an array of x values. I can give it a central x value, so this is a scalar value of x. I can give it a width sigma, and I can give it a central momentum or an average momentum value, and what it will return for me is a complex array of wave packet values. And so let me just show you briefly what that function looks like. So I have over here somewhere my Gaussian wave packet function. So this looks, surprisingly like what the math would look like, right? I just have to define my little prefactor for my Gaussian, and then in terms of my arguments, I can just evaluate that function. And the cool thing is, you'll notice I'm passing, well, you might not notice, I'm telling you that I'm passing an array of x values. So this first argument is actually an array. And so what will happen is I'm going to call numpy.exp. X can take as an argument scalars or arrays, and if you give it an array, it's going to evaluate the exponential at each value of that array. And of course, if you give it an array and it evaluates the function at each value of the array, the result will also be an array. So what we'll do is we'll define an array within this function, and we'll return that array as the completion of the Gaussian packet function. So when I actually call Gaussian packet the function and give it an array of x values, what I'll get back is an array of Gaussian wave packet values, which is pretty cool. Okay. So here are the values that I'm going to, when we actually write the code, these are the values that I'll actually use for the central position value, the central momentum, and the spread in space for the wave packet. Okay. The next thing that I need to do is basically I need to consider how many terms are going to be in my expansion of particle in a box um, how many different energy eigenfunctions I'm going to use in my expansion of the Gaussian wave function. So I'm going to create an array, which I'll call n, between 1, which is the lowest energy, which is the lowest quantum number for the particle in a box, up to some maximum value, big N. And of course, the goodness of the fit is going to depend to some extent on how large n is, because I might need many components to reproduce my Gaussian wave packet. Okay, so once I have my array of different quantum numbers, what I want to do is I want to actually determine the complex amplitudes for each one of my energy eigenfunctions between 1 and n to most closely approximate the Gaussian wave packet. So I have also written a function custom called Fourier Analysis, right? Because what am I doing? I'm making use of a Fourier series to approximate the Gaussian, so that's why I called it that. Why I called the function that determines the coefficients Fourier Analysis. And so you can see the code here. I'm going to post when this YouTube video goes up, I'll make sure you have a link to this actual code. So that's why I'm not going to take you through every single little detail of everything. Okay, so anyway, I'll call Fourier Analysis to get an array of coefficients. Once I have those coefficients, then what I can do is I can go ahead and build my approximation to the Gaussian wave packet, which I'll call psi underscore exp for expansion of psi. And then finally what I'm going to do is I'm going to plot psi and psi exp to visualize how good my fit is. Okay. And so we're going to try to go through this outline here in the code with, knowing that these functions are already built. And so I have to confess it's a little bit awkward to try to write code and talk at the same time. So of course I have, some of my favorite bed music all queued up. We're listening to dots and loops here. And so I'm just going to kind of go through this outline, and I'll comment from time to time, but there may be sort of like moments of silence where I'm just typing, and hopefully, the bed music will keep you from cringing too much with the silence. Okay, so let's get started. So the first thing that I want to do is I want to define a value of L for the length of my box. And then what I want to also do is create my X grid. And so what I've done here, so the length of my box is 500. So my X grid should go between x equals 0 and x equals 500. And how many x values I'm going to have is given by this number. So that means, of course, dx is going to be L over 2000. Okay, so yeah, this is a evenly spaced grid of x values between 0 and L, and it's 2000 x values. Okay. So the next thing that I'm going to do is I'm going to define these constants that deal with my Gaussian wave packet. So my central position, my average momentum, and the spread of my wave packet. And I'll remind everybody that I'm using atomic units one more time. So all of these things, K naught, by the way, what is its momentum? Well, you should always be able to get the actual value of momentum in quantum mechanics from Planck's constant times your wave vector k. So h bar k naught should be the average momentum. And what's h bar in atomic units? It's 1. So what is the average momentum of this wave packet? It's 0.4 atomic units. Okay, excellent. So I think that's basically everything I need for my Gaussian wave packet. I just actually need to call the function to create my array of Gaussian Wavepacket values. And so hopefully that was called correctly. Okay. Next thing I'm going to do, so we want to start building up an expansion of particle in a box energy eigenfunctions that approximates this Gaussian wave packet. So I need a couple of things. One thing I'm going to do is I'm going to create an empty array, which I'll call psi exponential, and psi exponential is going to be an array of zeros. And how many zeros will it be? It will be however long x is, that's how long I want psi exponential to be. And I think, yeah, here we go. So the other thing is, what type of data is this in this array of zeros? They're going to be complex data, right? So I don't want to just initialize this as the real number 0, but I want to initialize every value as 0 plus 0i. Because in general, psi exponential is going to be filled with complex values, just like the array psi, big psi, is filled with complex values. And finally, I need to determine how many different terms are going to fit in my expansion. So I want to make an array of possible quantum numbers between 1 and some maximum number n. So let's start with 50. So basically, this is going to fill an array. It's going to create an array called n, and it's going to fill it with numbers 1 through 50, and there's going to be 50 possible numbers. So that means that, you know, basically you're going to have 1, 2, 3, 4, 5, all integers up to 50. Okay, and one thing that'll be interesting will be to see, you know, how good is the fit using the first 50 energy eigenfunctions. Might turn out that we actually need more. Okay. So now I'm sort of done with step 3 of my outline here. So the next thing that I want to do is I want to determine the complex amplitudes for these various energy eigenfunctions that make up this big psi. So I'm going to call my function Fourier Analysis, and I'm going to give it the arguments x, psi, n, and l. And so if everything is working correctly, what Fourier Analysis should do is return yet another complex array where each element of that array is the expansion coefficient for the corresponding energy eigenfunction. So the first element would be the complex expansion coefficient for energy eigenfunction 1. The 50th would be the complex expansion coefficient for energy eigenfunction 50. Okay, so those are those are basically the amplitudes, the complex amplitudes that I need to approximate big psi in terms of my energy eigenfunctions. So let's go ahead and let's build our superposition using those complex amplitudes. So I'm going to do a for loop here where I loop through all of the values of C sub n. And I have another function called PIB underscore func. I need to remind myself in what order I want to call, what order I need to put the arguments in. So PIB underscore func, you give it your array of x values, the quantum number, and the length of the box, and it returns for you an array of the function values. So X, N, and L is the order. Okay, so that should do it, right? So we're going to go through every value of our complex amplitude array, and we're going to say that psi exponential is equal to the previous value of psi exponential plus complex amplitude times the corresponding energy eigenfunction. And of course, we initialize psi exponential to be an array of complex zeros. So, so the first time we go through this loop, the first iteration, right, we're just going to get 0 plus coefficient of, or the amplitude behind energy eigenfunction 1 times energy eigenfunction 1. Okay. So if we haven't made any mistakes yet, we are through step 5 and on to step 6, which is the final step for this tutorial. We simply want to visualize the Gaussian wave packet we built and then the expansion that we built in terms of the energy eigenfunctions and see how closely they match. So I'm going to use this built-in capability of the module matplotlib. I'm going to first create my plot object using this function plot plt.plot, and then I'm going to show you the plot. And let me just, before I do that, let me just go up to the top and show you that I have actually imported NumPy as NP and matplotlib as PLT. So when I'm calling plt.plot, I'm using the function plot within the matplotlib module. And when I call np.linspace and that sort of thing, I'm using functions within the NumPy module. Okay, so back down to the bottom. If this works, and if it works, I'm going to go back and explain the last couple of steps. So I'm going to save, and then I'm going to try running my program. Okay, I'm getting an error. Seems to have something to do with an array being of the wrong length. Ah. Yes. Okay. So a little explanation for that error. Let's see. Let me see if I fix the error first of all. Yeah. So we fixed the error. Excellent. So let me explain what that error was about. Somehow my terminal has gone crazy. Okay. No worries. Okay. So one thing I forgot is that the function that I made to return the particle in a box energy eigenfunctions, it does take an array of x values, but it takes a scalar value of the quantum number n and a scalar value of L. Previously, I had actually passed the array in to the function when what I really wanted to do was pass the scalar value of n. And so in this loop, what I'm doing, right, is that I'm going through specifically through the elements of, or I've designed the loop to be bounded by the elements of this array Cn, but Cn has the same length and is ordered in exactly the same way as the array n, right? N is the array of integer quantum numbers, 1 through 50, and Cn is the array of complex amplitudes for each particle in a box energy eigen function 1 through 50. So they're ordered in exactly the same way. So C of n sub 0 would be the amplitude for the first energy eigenfunction, and n of 0 would be the number 1, corresponding to the quantum number for the first energy eigenfunction. Okay. So that was a mouthful, but that took care of that last little error. And then plot this plot command. What I wanted to tell you is that, at least to the best of my knowledge, you can load this up with as many arguments as you want, in the sense that, well, I shouldn't say that. Let me backtrack. What are these first three arguments refer to? So the first argument is actually the array of x values. So this is the x-axis. The second argument is the array of your function values corresponding to the x values. So this is basically your y-axis. And in particular, this Gaussian Wavepacket, of course, is a complex number. So what I'm doing is I'm using the function numpy.real to take only the real part of the Gaussian Wavepacket values. And then this right here is like a style argument. And so I really don't know a whole lot about this matplotlib yet, but what I do know is that this will create a blue dashed line. So B for blue, and then these things are for dashes. Okay, so if I just ended this function here, right, I would just get a plot of the real part of the Gaussian Wavepacket plotted with blue dashed lines. But I can keep going, and I can then give it the same array x, and then np.real of psi underscore x for my fit, or my expansion of particle in a box energy eigenfunctions, and then one more style command red. And so what that will do is plot both the Gaussian Wavepacket in blue dashed lines, and then your expansion in red lines. And then plot.show just simply brings up the actual plot. And so let's look at the fit. So you can see red is our expansion, blue is the actual Gaussian Wavepacket. The fit's not so good. So this could be a deficiency in the number of terms in our expansion. So to test that idea, we'll simply make our array of quantum numbers twice as large. So now we'll include the first 100 energy eigen functions in our expansion, and we'll determine the coefficients for all of those terms, and then we'll build our expansion in terms of all 100 of those. So let's save and try that. Okay. So now the fit took slightly longer, but you can see that it's substantially better. In fact, you really cannot see any error at all between your expansion in red and the underlying Gaussian function in blue. So that basically wraps up part B, where we're creating an expansion and visualizing it. And then all that remains is what we'll do in part C, which is we'll actually animate these things using the animate function of matplotlib. All right, stay tuned for more.